Understanding slope and intercepts is fundamental to interpreting linear relationships across mathematics, physics, finance, and data analysis. These concepts form the foundation for analyzing how variables change in relation to each other. Let's begin by examining a coordinate system where we can visualize linear relationships. Every linear equation creates a straight line that can be described by two key characteristics. This straight line represents a linear equation. Every linear equation has two fundamental properties that completely define its behavior: the slope and the intercepts. The y-intercept is the point where the line crosses the vertical y-axis. This represents the value of y when x equals 0, providing a starting point for understanding the relationship. The x-intercept is where the line crosses the horizontal x-axis. This shows the value of x when y equals 0, indicating another key point in the linear relationship. The slope measures how steep the line is and in which direction it moves. It represents the rate of change, how much y increases or decreases for each unit increase in x. These fundamental concepts of slope and intercepts are essential tools for understanding linear relationships. They appear in mathematical analysis, financial modeling, physics calculations, and data interpretation across numerous fields. In the following sections, we will explore detailed methods for calculating slope and intercepts, examine their properties, and discover their practical applications in solving real-world problems. The slope, denoted as m, is a fundamental concept in linear equations that measures both the steepness and direction of a line. To understand slope, we need to examine four distinct types. First, let's look at a positive slope, which indicates that the line is ascending from left to right. A negative slope indicates that the line is descending from left to right. As we move from left to right along the line, the y values decrease. A zero slope represents a horizontal line. The line neither rises nor falls as we move from left to right, maintaining a constant y value. An undefined slope represents a vertical line. Since we cannot divide by 0 when calculating rise over run, the slope is mathematically undefined. The slope is calculated using the concept of rise over run. Rise represents the vertical change, while run represents the horizontal change between any 2 points on the line. Understanding slope is essential for analyzing linear relationships and forms the foundation for more advanced concepts in algebra and calculus. The x-intercept is a fundamental concept in linear equations. It represents the point where a line crosses the x-axis on a coordinate plane. By definition, the x-intercept occurs when the y-coordinate equals 0. At this point, the line intersects the horizontal x-axis. Let us examine this concept using a coordinate plane. We will plot a line and identify where it crosses the x-axis. Consider the linear equation y equals 2x minus 4. We will use this equation to demonstrate how to find the x-intercept. The line crosses the x-axis at this point. This is our x-intercept. Now let us determine its exact coordinates using algebra. To find the x-intercept algebraically, we set y equal to 0 in our equation and solve for x. First, we substitute 0 for y in our equation, giving us 0 equals 2x minus 4. Next, we add 4 to both sides of the equation, resulting in 4 equals 2x. Finally, we divide both sides by 2 to isolate x, giving us x equals 2. Therefore, the x-intercept is at the point 2, 0. The x-coordinate is 2 and the y-coordinate is 0, confirming that this point lies on the x-axis. In summary, finding the x-intercept requires setting y equal to 0 in the linear equation and solving for x. This method works for any linear equation and provides the exact point where the line crosses the x-axis. When finding slope and intercepts from a graph, we begin by examining the visual representation of the linear equation. The coordinate plane provides all the information needed to determine these key characteristics. The first step is to identify two distinct points on the line. These points should have coordinates that are clearly readable from the graph. Here we can identify the points 1, 1 and 4, 3. To calculate the slope, we use the rise over run method. The rise is the vertical change between the points, and the run is the horizontal change. From our points, the rise is 2 units and the run is 3 units. Using the slope formula m equals y2 minus y1 over x2 minus x1, we substitute our coordinates. This gives us 3 minus 1 over 4 minus 1, which equals 2 over 3. Therefore, the slope is 2/3. The y-intercept is found by identifying where the line crosses the y-axis. This occurs when x equals 0. From the graph, we can see the line intersects the y-axis at the point 0, 1/3, so the y-intercept is 1/3. Reading directly from the graph, we have successfully determined that the slope is 2/3 and the y-intercept is 1/3. This visual method provides an intuitive understanding of how linear relationships are represented graphically. To find the slope and y-intercept from a linear equation in standard form, we need to convert it to slope-intercept form through algebraic manipulation. Standard form is written as ax plus by equals c, where a and b are coefficients and c is a constant. Slope-intercept form is written as y equals mx plus b, where m is the slope and b is the y-intercept. Let's work through a specific example to see how this conversion process works. We start with the equation 3x plus 2y equals 6. Our goal is to isolate y on the left side. Step 1, we subtract 3x from both sides. This gives us 2y equals negative 3x plus 6. Step 2, we divide both sides by 2 to isolate y. This gives us y equals the fraction negative 3x plus 6, all divided by 2. Step 3, we simplify by distributing the division. This gives us y equals negative 3/2 x plus 3. Now we can clearly identify the slope and y-intercept from our slope-intercept form. From our final equation, y equals negative 3/2 x plus 3, we can identify that the slope m equals negative 3/2 and the y-intercept b equals 3. The key to converting from standard form to slope-intercept form is to isolate y by moving all x terms to the right side and dividing by the coefficient of y. This reveals the slope and y-intercept directly. In data analysis, linear regression serves as a fundamental tool for identifying and quantifying relationships between variables. When we have a dependent variable that we believe is influenced by an independent variable, linear regression helps us model this relationship mathematically. Consider this example from business analytics. We have collected data on advertising spend and corresponding sales revenue. Each point represents one observation, showing how much was spent on advertising and the resulting sales revenue for that period. Linear regression finds the best fitting straight line through these data points. This line, called the regression line, represents the mathematical relationship between our variables and follows the familiar slope-intercept form. The slope of our regression line provides crucial insights into the relationship's strength and direction. In this example, the slope of 4.5 tells us that for every additional $1,000 spent on advertising, we can expect sales revenue to increase by approximately $4,500 on average. The y-intercept reveals the baseline value of our dependent variable. Here, the intercept of 4 represents the expected sales revenue of $4,000 when no money is spent on advertising. This could represent organic sales or baseline business activity. We can visualize this intercept as the point where our regression line crosses the y-axis, representing the predicted value when the independent variable equals 0. The true power of linear regression in data analysis lies in predictive modeling. Using our established relationship, we can make informed predictions about future outcomes based on planned inputs. For instance, if we plan to spend $7,000 on advertising, our regression model predicts sales revenue of approximately $35,500. This prediction is based on the established linear relationship in our data. Linear regression analysis provides data analysts with quantitative insights into variable relationships. The slope indicates the rate of change and relationship strength, while the intercept establishes the baseline value. Together, these parameters enable evidence-based decision-making and reliable predictive modeling in various analytical contexts.